In this video, I'm going to review how to carry out inferential testing with logistic regression. And before we do so, there are a couple of assumptions when conducting this inferential approach with the logistic regression analysis. And the first approach, which is often rather difficult to establish when you're conducting research studies, but the underlying assumption is that there was some sort of randomization process when the data were gathered. And the second assumption here, when applying this specifically to logistic regression, is that the data or the outcome variable models a binomial distribution. And once again, to review, the outcome variable is a dichotomous variable. And just to remember, the model that we're evaluating here has only one predictor, that's x, and it follows this general model for the population, where the logit, which is the logarithm of the odds, and it's predicated on the probability that the outcome will be a success, or y equals 1 is equal to alpha plus beta x. And what we're evaluating with inferential testing is the beta. And this follows a similar pattern we saw with other regression models when subjected to inferential testing, is that we evaluate the null hypothesis that the beta is 0 versus the alternative that the beta is not 0, so is significantly different from 0. And this is referred to as the test of independence. And in the event that the null hypothesis is true, with the beta equals 0, that would imply that our predictor, which is x, has no effect on the probability of a success, which is y equals 1. And so what we conduct here, after we finish up with our logistic regression analysis, is we take the next step to make this take this inferential approach. Now, the question here is, how do we test the null hypothesis? There are two statistics that I'll be addressing here in this lecture, in this video, and that's the z-test or the Wald statistic. On this slide, I'll cover the z-test. And so, giving our hypothetical data here, we have our beta hat, which is the which is the statistic generated from the sample. This is unique from the model in that the model is the foundation to evaluate the sample data, and that's why we use the hat symbol to differentiate that these are hard numbers obtained from the data and not a theoretical model. But given our hypothetical data of a beta equals 0.105, the statistical output will also return a standard error for this beta value for our estimate of the slope in our equation. And carrying out the z-test, the equation here is just simply the ratio of the derived beta, which is the value you see here from the data, divided by its respective standard error. The accompanying video with this analysis obtained with SPSS will demonstrate where to get these specific statistics. But the z-test here will just simply take the ratio of these two outcomes, and we see that when we divide the beta hat by its respective standard error, we get a z-value of 4.02, and now we can take our z-value and compare this against the critical z-value of 1.96. And we would, since the 4.02 is larger than 1.96, then we can reject the null hypothesis and conclude that the beta is not 0, which would demonstrate a statistical correlation, a statistically significant correlation between our our predictor variable, and the outcome, which is the probability of success or failure. The second statistic here, I'll just briefly cover on slide number 3 here, is the Wald statistic. And the Wald statistic is just simply the square of the z statistic we calculated on slide number 2. So here we have the same values of 0.105, which is the beta value obtained from the data divided by its respective standard error. We then take the square of that value, which would be 16.2. And this is not based on a z or normal distribution. This is actually based on a chi-square distribution with a degree of freedom of 1. And the symbol for chi-square is Greek letter chi squared. And in the accompanying video, you'll see how we can do this with SPSS, and you'll find that the Wald statistic will also demonstrate that it is statistically significant in terms of the relationship between our predictor in these hypothetical data and the outcome, which is the probability of success or failure.